Alright, before we start on acids and blood buffering, I just want to make sure that we've got the ionic and covalent bonding sorted. In fact, it's actually a line of variance, if you like, a spectrum. At one end, where the difference in electronegativity is very high, for instance, the difference between fluorine and lithium here is very great. The difference between chlorine and sodium, very great. And here we've got our sodium chloride, which we know is an ionic bond. We've put it in water ourselves. It falls apart straight away, and that's ionic, and that's not a problem. If we move down the scale of difference, we've got a polar covalent bonding here and here, where oxygen is hogging the electrons close to it, leaving a bare backside of proton exposed, a positive charge, making the molecule slightly negative at one end and slightly positive at the other end. And that's a polar molecule with polar covalent bonds. Then, if we move and the difference is very, very low, and the difference between carbon and pretty much anything is not very great, and so carbon has to share equally. And so this is a non-polar molecule, therefore not soluble, remember, because it has a bearing on solubility. And so this has got shared electrons. It's a non-polar covalent bond. None of that is argued over. Here we've got oxygen, which we know doesn't share electrons nicely, but in this case they're pulling equally on the electron, so the electron has to be shared in the middle. So even though oxygen doesn't share nicely when it's sharing with itself, it still has to be a non-polar molecule, and it's a non-polar covalent bond. The tricky bit is when it comes to in between. How do you judge? And when you look at a molecule as complicated as sucrose here, you can see that it gets harder and harder to judge. And we talked about this last Tuesday. Generally, when you see a whole load of oxygen atoms, it's going to be soluble. If we look, however, at hydrogen and chlorine, the difference in electronegativity between the chlorine and the hydrogen atom is very, very great. And you're going to say to yourself, I know that's an ionic bond. What I'm going to tell you is that it's an extremely polar bond, and the reason for that, in its simplistic terms, is that this is between two gases, and an ionic bond is between a metal and a non-metal. However, mathematically, of course, it's exactly the same, and practically it's exactly the same, because as soon as we drop this hydrochloric acid molecule into water, it's going to dissociate, and that brings us to hydrochloric acid, which is a strong acid. A strong acid, remember, has got nothing to do with its concentration, but has got to do with how likely it is to ionize. I bung some water in here because you don't get hydrochloric acid that's not aqueous. The most concentrated you can get it is about 68%. This is what it looks like inside your tummy. Well, actually not quite in your puku. Not quite, because it's a strong acid. It dissociates. So this is what it's going to look like. Oops. I want to pull the protons off. Remember, hydrogen is just an electron and a proton, nothing else. So when it dissociates, you're just left with the proton out of the hydrogen, and so there it is, completely dissociated, or 99% dissociated. So I'll put one back on. So that's more in reality what it looks like in your stomach. You need that because you need to break down the molecules of your food, and that's what is helping to do that. If we just look at this, the number of protons is what relates to the pH of the liquid. The pH is low when there are lots of free protons. I didn't invent that system. That was invented by a Swedish bloke. But the more protons, the more hydrogen ions there are, the lower the pH. So that's a strong acid, and that's in your stomach. If we look at carbonic acid, which is the blood buffering system, this is the kind of acid that you've got in your blood, carbonic acid. Again, of course, that's in water, in your blood, but I'm going to take the water molecules away because they're too similar in colour. In reality, because carbonic acid is a weak acid, hardly any of it is ionized. So that's the difference between a strong acid and a weak acid. In this case, hardly any of it is ionized. So, blood pH needs to be very tightly controlled within 7.35 and 7.45 pH. That's a very narrow band. Outside of that you die, so it's quite important. And so we're just going to look at how that works. This turns up, the blood buffering question turns up in both the chemistry test and in the biochemistry test. So you do really need to know how this works. So if our blood is normal in terms of pH, i.e. between 7.35 and 7.45, then everything is sweet. But supposing we had a whole rush of dissociation here. You could do this yourself by taking an overdose of aspirin, which I don't recommend. Or you can hyperventilate, all these things. So if we had a whole load of hydrogen ions here, then we will have a very low pH. What can we do to fix that situation? Well, we can mop these up. We can reform the acid. So it's not the acid, the whole acid, that's causing that horrible, painful, acidic burn. It's these things that are causing that problem. So how do we balance it? How do we write it? In our equation, we'll have carbonic acid on one side, fully formed carbonic acid on one side. We'll have this, remember, is the bicarbonate ion. If you remember from the table of common ions, this is the one I asked you to remember. Here's our extra electron hugging onto that. There is the proton that is lost from it. So if we've got too many, we'll mop them up by reforming more and more. I just don't have enough molecules, but we'll reform more and more to deplete this pool and make the pH rise again. Supposing we've got insufficient hydrogen ions, and so we have got high pH, then the way we can fix that is by more acid dissociating, dissociating, and that way we are lowering the pH again. So this will be buffering back and forth, and so you can see that it doesn't matter which way the reaction is going, it goes equally in both ways to keep that at just the perfect level between 7.35 and 7.45. So we can talk about that later. Hope that explains it for you.